So here is plan of my talk. I will talk about actually Voevodsky vision of this project of, more generally of project of foundations of mathematics, his work in foundational mathematics, and it actually has two parts which you see, and then I'll try to place Univalent Foundation in the existing form and actually trying to relate it to this second task, which normally is not directly addressed by Univalent Foundation, but I make such a speculative and rather philosophical attempt to do this and to see some perspective and then come to conclusion and some open problem. No, so as I say, it's absolutely typical that work in foundational mathematics is motivated by some philosophical ideas or at least some strategic vision, say, of mathematics, and certainly that is the case of Univalent Foundation. So here I refer to Vladimir's talks. They are now recorded and available on his Princeton Institute webpage, made in November, December 2003. So that was before actually anything like Univalent Foundation emerged. And the question he posed, what is the most important task for mathematics in the near future? And his answer had two parts. And first part was to develop kind of a computerized version of Bourbaki, and that's actually what Univalent Foundation issued from, first of all. But there was also second part, which was his concern of making better connection between pure and applied mathematics. And now I briefly talk briefly about these parts in terms, just short disclaimers that, of course, by doing this, I'm not, I don't want to say that any mathematical idea since it emerged and is born is somehow doomed to be developed only along some original motivation. Of course, it could be different motivation, can be developed in different directions, but I still think it's interesting to not forget this kind of original motivation and trying to place further strategies somehow against this background. And second, of course, that's just my understanding of Vladimir's ideas, so maybe not fully adequate somewhere. And third part, there is a part of this which is actually mine and not Vladimir's, and that's rather easy to separate. So this idea of computerized Bourbaki, and actually Bourbaki is kind of a new version of Euclid's elements. So Bourbaki was certainly, this name, Éléments de mathématiques, was inspired by Euclid's. And so I also, since I worked on Euclid for my PhD thesis, I somehow see this as a further kind of computerized version of Euclid in that sense. And but they're all more specific desiderata. So Vladimir specifically emphasized the need of better encoding of informal mathematics into formal language, and he argued that this standard set theoretic foundation are simply maybe good for other reasons, but not for that specific reason. Specific idea was to encode this informal mathematics into formal calculi and the computer code, which would allow for effective formal proof checking. It's again something that doesn't really work with standard formalizations. And actually that I added from myself some form of modularity. So if we have this big foundation mathematics, I think it's a requirement for all foundation mathematics. We need to shuffle somehow different blocks, and probably problem here is this all this proof relevant philosophy or ideology of Univalent Foundation in a sense makes certain tension with modularity where we need on the opposite somehow just take results and at certain point forget their proofs. But I will not discuss this. So I assume that in its existing form, at certain degree, Univalent Foundation satisfies this desiderata, and it's not my task now better evaluate and improve it. It's only to point that Univalent Foundation just developed so far in more or less in that direction. But here I would like to mention the following, that when Vladimir discovered for himself Martin-Löf type theory, and he did this via looking into proof assistance, actually Martin-Löf type theory in its turn, it had a very strong philosophical background in work of Doug Pravitz, for example. Per Martin-Löf himself actually wrote quite a lot of philosophical papers and tried to ground that project on certain philosophical ideas. Very roughly, the idea is what Doug Pravitz calls general proof theory as opposed to Hilbert's type proof theory. And the idea is that it shouldn't be just a syntactic issue, a study of syntactic derivations, but somehow it should come with semantics, which today is called proof theoretic semantics. And here is just a quote from Martin-Löf. Actually, no, I will not read it, you can read it, but what I want to emphasize again, this idea that meta-mathematics is not what we want here in that project, right? And that actually fits very well to this pragmatic argument by Vladimir that standard foundation may be good for doing meta-mathematics, for getting important meta-mathematical results, but not at all for effective encoding of simply mathematics and making anything like formal proof checking. Okay, and actually here these two ideologies, if you like, fit and come together, but just in a minute later in my talk I'll point also to a point where they diverge, and that's, I think, it's something interesting. And here I only also refer to recent paper, actually it's not yet published, by Goran Zundolm. He calls it, I like very much the title, it's called The Neglect of Epistemic Consideration in the 20th Century Logic, and basically it's development of the same argument. He also puts it in a historical context, but I would like to emphasize that this kind of philosophical and historical issue, I think, have very direct effect, kind of practical effect on mathematics and also on computer science. For example, in computer science, ontology became something familiar, right? Just people do ontologies in computer science. It even becomes a commercial product. I know people who do writing ontologies just for earning money. But formal epistemology, first thing, of course, it's not that well developed as formal ontology presently, but it, to the best of my knowledge, simply does make part of knowledge representation methods in computer science, which of course is strange if you think that we are talking about representation of knowledge, right? It's like we should take care about epistemology at the first place, and I think that's really, albeit indirectly, it's kind of effect of this general understanding of logic which was dominating in 20th century, which Goran criticizes in that paper and points to this neglect of epistemic consideration. And I think it's more practically, probably that could be just for a different talk, but I think that standard architecture, as far as I know, of this knowledge representative systems simply doesn't allow for regular users to verify what they are supposed to learn from that system, right? So it somehow is up to engineers or people who install that system, but there is no procedure which, as far as I know, which really allows users to justify their beliefs. So it's all just about creating true beliefs, but not about making justified for individual users true beliefs. And so I think there is a good hope to improve it using this architecture. Okay, so now I turn to the second part, and that's about this bridging pure and applied mathematics problem that was actually in the same Vladimir's talk. So what is the problem? The problem is that he just observed that there is a lot of interesting and important for pure mathematical objects like category shifts, cogomology, simplicial sets he mentions, which are not used outside mathematics, or very little used perhaps, right? And Vladimir thinks it's a problem, but it's interesting how he thinks, first of all, his project is not somehow subdue pure mathematics to practical needs, not at all. He values very much this mathematical freedom, So he says, that's not the way. But still, he thinks that all these channels, this is his picture, rather usual, I would say, conventional thinking, it's kind of just real-world problems, say, right? And then some of these problems are solved via mathematical modeling. And then there is more abstract level where mathematical problems are put and solved just for their own sake. And still he believes that these channels are very important for everything, both for pure mathematics, that it works properly, and of course for all kind of practical issues. But here he says, okay, today we have this new element, computer modeling. I would say it's absolutely new element. Historically speaking, I think something like measurement and computing all the time served as a channel between, say, pure mathematics and applied mathematics. But today he kind of stressed this fact, and this is interesting, where he looks for a solution. He says that presently we translate from computer modeling to foundational mathematics, which is before Univalent Foundations, so it's supposed to be set theoretic at that stage, via, say, informal mathematics. And he wants kind of shortcut, kind of direct access from computer modeling to foundational mathematics, and he believes that that can really improve the situation. So the picture would be like this, and he says, right, that we need to reorganize this layer, he calls it, between computer modeling and pure mathematics. And that's interesting because, look, if you now compare these two projects, say, proof verification, computer-assisted proof verification, and this bridging, then the method is the same, making better connection between foundations and computation, except, of course, there is some different indirection. In the Univalent Foundation, rather translate from foundation to computation, and here perhaps we need a opposite translation, but for the moment I just ignore this subtlety, which may be interesting. And I'm trying just to consider Univalent Foundation as possible candidate, not only for accomplishing this new Bourbaki task, but also kind of key solution for this bridging task, or some version, something like Univalent Foundation. Okay? And so one way to do this is what Urs Schreiber and some other people are doing. It's develop a mathematical foundation of physics, but I'm trying a different approach, which rather relates to computer science. And I will talk about Univalent Foundation as kind of representational framework, and not even I will talk about computer science, knowledge representation in the sense of computer science, but rather there is a philosophical discussion about formal representation of scientific theories. So I go briefly to this discussion. And actually, there are two approaches which are discussed. One very old, which is called today syntactic, even it was not self-description. Actually, it refers to early attempt to axiomatize different theories. It's like Hilbert's sixth problem. It's axiomatized physics, axiomatized biology, and some people like Ernst Nagel did some work in that. But next generation of people with Patrick Suppis and Bas van Frassen, who continues that program, was dubbed semantic approach, or also they call it non-statement view. And the idea is here that the slogan is that scientific theory is simply not a list of statements. It simply cannot be identified with any syntactic presentation, but rather should be identified with a class of models. Right, but still the general idea is the same, because they still use the same kind of first-order theories mostly, and say Tarski style model theory. So actually this kind of conflict between these two views, some people argue, and I agree with this more recently, that there is no conflict, it's just that these people of younger generation learned something like formal semantic, which was was unknown before the war, and that's the whole issue is about. So we should not, make a choice between these two versions, but develop something synthetic. But I still want to try something different, which I called constructive architecture. And the idea is here is actually kind of model after Univalent Foundation. And the idea is use a Gensen-style architecture rather than Hilbert style. And so the idea is that rules, formal rules, may be informative in the sense that not necessarily their semantics should be logical in some very general sense, right? It may simply be specific for certain theory. And actually, I also remarked, which is kind of underdeveloped dimension, not completely unknown, of what Hilbert called axiomatic freedom of constructing new theories, because of course today we have many logic and we are not stick to some fixed, say, logical semantic, not only model ponens as in Hilbert, but still, since we are talking about logic, it's supposed to be something very large. Why I think it can be quite specific just as a theory, which is specific about certain domains. So this is the idea. And okay, there are some obvious advantages, like it may facilitate computational implementation, and the key idea that allow for representing various methods, or as epistemologists also say, knowledge how, including theoretical, empirical methods of verification of statement, which are certainly, unlike some methods of discovery, they cannot be put off as, say, not related to accomplished knowledge. They do make part of accomplished knowledge, and here, yeah, I think it's also very important that such a representation may support thought experimentation, experimental design, which I think it's really important for science. And there are actually motivating examples which come from the past. I don't have time to develop that, but actually we look closely and with kind of scholarship attitude to Euclid, it is a Gensen time system. Those so-called axioms, which Euclid called common notion or postulates, they are all rules. They are not sentences with truth values. And we also look into Newton Principia, which is also modeled after Euclid. I didn't study that example as thoroughly as Euclid, but it looks again that it's all about methods which really make part of logical structure. They are not kind of external devices only. And of course, if we look just I took quantum field theory, it could be any other theory comprises a lot of different methods, and which includes both mathematical methods and experimental methods. And if we are asking whether these methods play a logical role, and I think the answer isn't positive, because these methods provide evidences, so proofs in this general sense of general proof theory in line of Pravets and Martinov. Okay? And so what really homotopy type theory does specifically for that? Because so far I just said very general things. But I think it's very interesting, this idea of homotopy level, right? If we took it seriously, that actually allows us to distinguish between some logical level in restrictive sense of logic, which deals with propositional type, and all high types, which serve which provide proofs in that sense, evidence for these propositional types. Okay, and actually that does not fully agree with what Martin Löw had in mind in '84. Because at that point he tried to interpret all types uniformly. And he just said there are kind of alternative interpretations for any type. We can interpret terms as elements of set and as a proof of proposition, or something like method of intention or method of solving problem. It's like a-la Kolmogorov. And even he has a quote which he speculates per Martin Löw that if we think seriously, we kind of discover that set and proposition is just the same thing. And I think Hart very, very nicely shows us and gives us really mathematical argument that if it is not the same thing, right, that we really restrict proposition to zero types and all other types are high types. And actually, it's something like of blasphemy, which I'm going to say, but actually, if we have a higher types and something proposition on this above form, like here, right? T is an element of big T. So I'm not sure that there is really justification to call such things judgment. No, at least if we want to be serious about this term judgment as Per Martin wants to be, kind of philosophically serious. So perhaps, no, I really would like to discuss that. Probably I missed something really important here, but I think it would be more probably appropriate in such cases just call it declaration and not a judgment. Okay? So to conclude, what is this constructive view? As a philosophical view is certainly not new, but I think it's interestingly that earlier we just didn't have any interesting mathematical means to support such a view. But the view is just that theory is a bunch of methods and kind of class or category rather their applications. And applications are procedures which bring about evidences, and here I mean also empirical procedures, not only theoretical mathematical procedures, which prove certain statements. So whether a method works or not is actually a matter of empirical test, it's not something pre-decided. And so I come to conclusion that, okay, that's something worth to be explored. And finally, open problem. Many people, when we talk about Hilbert style, Gensen style, they're really saying something that is a matter of style. So they're saying it's a kind of superficial differences. So I try to study more systematically in which sense in any this Hilbert style, Gensen style theories can be equivalent. Okay, and it's easier to study this on the syntactic level, something like deductive equivalence, and still I think generally this Gensen style theory have no Hilbert counterparts. And more difficult question is actually semantic, how we translate between proof theoretic and model theoretic semantics. So all these are, I think, interesting open questions. I kind of criticize him because we talked. It's great work he was doing, but actually what he did in his reconstruction, actually his paper is called "Meaning Explanation for Hot," right? And I think he kind of confused between that's maybe he confused deliberately, and in my view it's justified. So I don't think that we should today really develop this project of meaning explanation as something different from model theory. We should do model theory. Here I agree. But then when he really describes explanation, as he called it, otherwise it could be called model, I think, of rules of Hot, right? He really interprets assumptions as judgments in usual sense, so something having truth values, and that's in his paper. And here I think we really lose something important. Of course it works. It works in kind of meta language, right? But that move does not preserve this feature, which I kind of think that can be very useful. You see this distinction between and combination of propositional and non-propositional levels. First of all, I think that's something traditionally done, right? Euclid did exactly that. He made it a library, and there was kind of difficult management, of course. And the same with Bourbaki. And of course, I think it's great to do it first with computer, and second with this additional feature, which in a sense brings us probably closer to Euclid, which really allows to give a standard for proof, not just making meta-theoretical vision of this. I think that's really, really very important. But no, I think it's rather for really mathematicians to teach me what are difficulties. I would like to actually know more how Univalent Foundation works across different mathematical fields, because I know more like stories of success, but probably it's interesting for this general evaluation also know about fields of mathematics when it doesn't work, probably for some reasons.